Alright, welcome back. Today we have text problem 28-59. So if you would, take out a blank piece of paper or a blank printout of the problem, and let's get started. So we have a current carrying loop with 5 amps of current running through it. It's in the shape of a triangle. And we have a uniform magnetic field at play, and the direction of that magnetic field is along the hypotenuse. So we have a uniform magnetic field at play, and it's asking us to find the magnetic dipole moment and the torque on the loop due to the current and the magnetic field. So let's do some writing in our read step. Lucky for us, there's only one equation that takes the magnetic dipole moment and the magnetic field into consideration. So our physics steps should be pretty straightforward. But let's visualize what's going on here with a sketch of the problem. Alright, so we have our 30, 40, 50 triangle, and as mentioned in the problem statement, the magnetic field is pointing in the direction parallel to our hypotenuse. And so notice that I have a magnetic field that's uniform, that this triangle or this loop of current is immersed in. Secondly, the current itself, in this case, is traveling counterclockwise, so it's going along the hypotenuse parallel to the magnetic field along the hypotenuse, and then traveling down along A and to the right along B. So it continues to travel in this loop indefinitely, unless there was some resistance in the wire that dissipates that electric current over time. With our shape, we also have the magnetic dipole moment. It is a vector quantity. The direction of that vector is always normal to the plane of your loop. So our loop is in the plane of our screen, and so the vector is pointing out of the screen. You can have it pointing in, it doesn't really matter. The only thing that's going to change is the direction of your torque vector. In this case, we have it pointing out. Alright, so let's continue on. Alright, so we're given the dimensions of our triangle, we're given the magnitude of the magnetic field, and we're given the current in our loop. So we look at our assumptions. We assume that there's no resistance in the wire, so once the current is in the loop, it will stay there and it doesn't vary with time. And the next one is the fact that we have one loop of wire. It doesn't say it implicitly, it doesn't say explicitly, so we imply that this triangle is just a single loop of wire, and that will have an effect on the magnitude of our magnetic dipole moment. So as far as the tasks that we're being given in the problem, the first one is to calculate the magnitude of the dipole moment, and our second task is to calculate the magnitude of the torque on the loop. Alright, let's move on to our physics step. I want you all to pause the video and write out the equations that you think you will need for this problem. Remember, the value of the read step can really significantly decrease the time you spend determining which equations you need. Alright, I'll see you in a minute. Alright, so how'd you do? Well, it looks like we're only going to need 2 equations for this problem. So if you have these 2 equations, then great job. If you don't have those 2 equations, then let's talk about why we need them. The first one is our magnetic dipole moment. And really this is a measure of how an unknown sample of material, if current passes through it, is going to behave in a magnetic field. We're going to see some torque acting on that object if it's aligned perpendicular to the magnetic field. And how much torque that material or that loop of electric current receives helps describe the magnetic dipole moment. So that describes what that is. We can calculate it by looking at the number of turns in our electric current loop, the magnitude of the current itself flowing through the loop, and the area that is swept out by the loop itself. So in this case, our loop is going in this triangular fashion, and it's the area inside our loop that we're referencing here in our magnetic dipole moment. Now, if you remember back to Gauss's law, or you remember our work with the electric flux, we had a differential area vector that was pointing normal to the surface in which our electric field was piercing through. In some cases, like in some of our suggested problems, the electric field was perpendicular to that differential area vector, which meant that there was zero electric flux through that surface, or it was parallel to that differential area vector and we had a maximum of the electric flux through that surface. So same concept in the direction of this magnetic dipole moment vector. And so when we go to calculate the torque on our loop, we can use that understanding to gather the direction of our torque. Now as we look at the torque equation, that shouldn't be anything new. The only thing that's changed are our two vectors that compose the torque. So we still have a cross product, but instead of the position vector of our force acting on a rotating body, we have our magnetic dipole moment. And instead of the force vector acting on a rotating body, we have our magnetic field. The same process will still apply. It's just different vectors. All right, so let's get into our solve step. All right, so part A, it's pretty straightforward. It asks us to calculate the magnetic dipole moment. From our physics step, we have our equation. And so it's really just a function of putting in the given information. So go ahead and pause the video and put in your calculation for the magnetic dipole moment, and I'll see you in a minute. All right, so first of all, we had to figure out what the area of our triangle was, and hopefully you remember your middle school experience or high school experience in algebra and geometry, and the area of that triangle is just 1/2 times the base times the height, and in this case we have B and A. As we put that formula into our magnetic dipole moment equation, we then put in our given values and we get 0.30 amp meters squared. So our current is measured in amps, so that's where those units come from. The number of turns is more or less unitless. It's just a number, and we assume that there's only one turn, so we only put a 1 in for that portion. Now, you'll notice that there's two sig figs here, and if you look at the problem statement, 30, 40, 50, and for the dimensions, and then the magnitude of the magnetic field is 80 milliteslas. Well, those are all just one sig fig, and the reason we went with 2 is often Halliday, Resnick, and Walker assumes that there is a dot after the 30. So just be careful with your sig figs in this case. We will be sure to be very clear on how many sig figs you will use on our graded events. So don't worry too much about that, but that's why we chose it to be 2 sig figs, which mirrors our 5.0 amps. All right, now for part B. We know that if we want to calculate the torque, then we need to do the cross product on our magnetic dipole moment and our magnetic field vectors. Now, before we get into it, of actually calculating this, let's first rewrite our cross product in terms of magnitude and angle. Now, the question is, when you put the cross product in the magnitude and angle form, it ends with a trig term, and the dot product also ends with a trig term, but they are different. So which one is it for the cross product? Is it cosine of the angle between our vectors or the sine of the angle between our vectors? Well, the answer is, according to our PRC on the back, bottom left-hand corner, is the sine of the angle between our vectors. And that results in the magnitude of the torque is equal to the magnitude of our magnetic dipole moment times the magnitude of our magnetic field times the sine of the angle between our vectors. Let me go back really quick. The answer to part A, first I have this in vector form, and then later I have it without any direction information. So let's clear this up and say that the magnitude of my magnetic dipole moment is 0.30 amp meters squared. Okay. Apologize for the mistake. Now let's get back to part B. We have the magnitude of the torque in terms of our magnitudes and angle. I want you to pause the video and draw a vector diagram for the angle between our two vectors in this problem. And I will see you in a minute. Alright, so I have two examples for vector diagrams of our vectors. The one on the bottom is more reminiscent of how we drew our diagram. Our other vector diagram, I've rotated the bottom one so that we can visualize our magnetic dipole moment vector and our magnetic field vector. The problem with that is that when we look at the direction of the torque vector, it's actually going to be pointing out of the screen. So we lose some fidelity on our 3D space on a 2D platform. So either one is acceptable, but the top one shows that, hey, I can see the angle between my two vectors and find that, hey, the angle between my vectors is in fact 90 degrees. And when we look at the sine of 90 degrees, we find that the result is just 1. So really, in this problem, the major factors are going to be the magnitude of our magnetic dipole moment and the magnitude of the magnetic field vector. Alright, so as you put in those two values, one from part A and one from the problem statement, we will have the answer to part B. So our answer is 0.024 Newton meters, and those are the same units that we used in our torque lessons prior to this when we were looking at pulleys and just forces acting on rotating objects. So even though we're in the electricity and magnetism portion of the course, it doesn't mean that our units on torque are going to change. Alright, so that's it for this lesson. I will see you in class.